Today we're going to discuss unit tangent and unit normal vectors. So this is a continuation of our discussion of derivatives, the applications of derivatives for vector-valued functions. Specifically today we're going to look at the motion of particles and how those particles, their motion can be described and specified by a vector function. So we need a few starting points. We will let r of t represent our space curve C. From our previous studies, we know that r prime of t will be tangent to the curve C at the terminal point of r of t, as long as r prime of t exists and is not equal to the 0 vector. Previous to this, we have used r prime to find tangent lines. So now we're going to build on that and find this idea of a unit tangent vector. So here's our definition. If we have a differentiable vector function on an interval I such that the derivative of the vector-valued function is not the 0 vector, then by definition the unit tangent function is defined as follows. So we see there we have capital T of t. So this is a vector-valued function. T of t is equal to r prime of t divided by the magnitude of r prime of t. And if you recall, whenever we divide a vector by its magnitude, we produce a unit vector. We know from previous sections that r prime of t will be tangent to the curve. Therefore, when we divide r prime of t by its magnitude, we have produced a tangent vector that also has a magnitude of length 1. Thus, we can call it a unit tangent vector. For our first example, let's let r of t be cosine cubed t, comma sine cubed t. So this is a two-dimensional curve, a space curve in the plane. We want to find the unit tangent vector t of t. From our definition, we see that t of t requires us to have both the derivative and the magnitude. Well, we can't find the magnitude without first finding the derivative, so our first step in this problem would be to find r prime of t. So r prime of t, by using the chain rule on each component of r of t and simplification, we get this expression for r prime of t. I factored the common 3 outside the vector. It is just a constant multiple, and we're left inside with negative cosine squared t times sine t and cosine t times sine squared t. Now we need to find the magnitude of r prime of t. So with magnitude, remember, we just need to take the square root of the sum of the individual components squared. And if we have a constant outside, as we do in this case, we can simply find the magnitude of the vector and multiply it by that constant, which is why we have here 3 times the square root of the first component squared plus the second component squared. Some really nice things happen for this particular vector-valued function when we carry out the algebra involved here. Notice this is just squaring each component leads to this plus this, and then factoring out what they have in common. It's a cosine squared t sine squared t. When we factor that out, we are left behind with a cosine squared t plus sine squared t, which is conveniently 1. Therefore, we have 3 times the square root of cosine squared t sine squared t. You may be tempted to make that just cosine t times sine t, but I caution that that's actually the absolute value of cosine t times sine t. Under certain circumstances, it would just be cosine t sine t. For instance, if it were in the first quadrant, if the t value were in the first quadrant. So finally, we want to get t of t. We need to divide r prime of t by its magnitude. So here's the magnitude. We found r prime on the previous slide, and so we get this divided by this. I have canceled out the common factor of 3 that would have been both the numerator and the denominator. And it's also possible to simplify this expression much more If, in fact, you know that cosine t, sine t is, for instance, in the first quadrant, then you could simplify the expression down to just negative cosine t, comma, positive sine t. Nice little two-dimensional simplified vector. But if we're not restricting ourselves to the first quadrant, we do need to make sure that we keep the absolute value symbols around that denominator. Now that we know how to find the unit tangent vector, we can move forward into looking at the unit normal vector. Just as the tangent vector is tangent to the curve at any given point, the normal vector, or unit normal vector, will be normal to the curve at any given point. So we're specifically going to be looking at what we call the principal unit normal vector. There would obviously be multiple normal vectors here, but the principal unit normal vector, which we're going to designate n of t, is always t prime of t divided by the magnitude of t prime of t. So in order to find the unit normal vector, you first find the unit tangent vector. We then use that result in the same processes to produce the unit normal vector, because we find the derivative of t and we divide it by the magnitude of the derivative of t. Dividing by the magnitude, once again, ensures that it's actually a unit vector. One other thing I want to point out here is that the principal unit normal vector always points into the curve. Obviously, there would be two choices for the unit normal vector. You could have gone this way, for instance, or the one that's indicated here. But this is the concave side, I guess, is what I would like to refer to that. So the value of n, if you do this computation, will always be pointing into the curve. So here n's pointing this direction and this direction, because that is into the curvature as opposed to outside the curvature. So something to keep in mind if you're using graphing software such as CalcPlot 3D to verify that you've done things correctly. Your principal unit normal vector should always point into the inside. Now together we can take the unit tangent and the principal unit normal vectors to define a plane. Particularly, this plane has a name. We call it the osculating plane. The reason it's called the osculating plane is it comes from the Latin word osculum, meaning to kiss. So the osculating plane will kiss the curve, essentially, right here. And if we have two vectors in the plane, that's enough for us to come up with the equation of the plane. Because we can use those two vectors to produce a vector that is normal to the plane. And in this specific case, we give the vector normal to the osculating plane its own name. We call it the binormal vector, and we give it the designation b. So b of t is the binormal vector to the osculating plane, and it is equal to the cross product of t of t and n of t. So we can find multiple things dealing with the projectile motion at any one point on a space curve. We can find the unit tangent vector. We can then use the results of that to find the principal unit normal vector. We can then cross t and n to produce the binormal vector, and then use the binormal vector together with the point on the plane of interest where we actually are to produce the equation of the osculating plane. So here's the, I guess, more fancy definition of the osculating plane. So if you need r to be a differentiable vector function, right? If it's not differentiable, you can't do any of this. And we need to make sure that t prime of t sub 0, so the point that we care about, t prime of t sub 0 cannot be the normal vector. That should be bolded because we're referring to a normal vector here. So that should not be equal to the normal vector. Then the binormal vector, as we just spoke about, is equal to the cross product of t and n, and the oscillating plane at r of t sub 0 is defined in this case. Let me move the picture up here temporarily. Now, what is this? this is the dot product form of the plane, right? If we dot the normal vector with a vector in the plane, it must equal 0 because the angle between those two vectors is going to be 90 degrees or pi over 2 radians. So this is the designation of any vector in the plane. If we take a general point x, y, z, and go from that point to the point p sub 0 or r of t sub 0, which has the coordinates x of t sub 0, y of t sub 0, and z of t sub 0. If we subtract the general point x, y, z and the specific point r of t sub 0, you would get this vector produced. And then if we multiply it by ABC, the components of the binormal vector, we would be doing that dot product to produce the equation of the plane. And here is a geometric representation of how all three of these vectors fit in and alongside a space curve. So we can see that t always points in the direction of motion. The particle would be traveling in this direction, as evidenced by this arrow right here. The principal unit normal vector always points into the curve, so it's on the concave side of this curve right here. And the binormal vector would need to be normal to both n and t, and so it would point up in this direction. And the osculating plane is not drawn on here, but it would be the plane that contained both t and n, and vector b would be normal to it. So as we have already referenced, vectors t, n, and b are three mutually perpendicular unit vectors, and they actually form a right-hand coordinate system, which has three different names if you run across these in your study of mathematics. The TNB frame, the moving frame, and the Frenet frame. So if all of these are synonyms for each other, and they refer to the unit tangent vector, the principal unit normal vector, and the binormal vector. If we work in a 2D system, the xy plane is always the oscillating plane, and so every binormal vector would be parallel to the z-axis. So it's just going to be a vector that has no x or y component, only a z component, such as this. B of t sub 0 would be just plus or minus k if you're working in a 2D system. And we're going to stop this video right here, and I will produce another one that gives an example of us walking through every step of this process to find the unit tangent vector, the principal unit normal vector, the binormal vector, and the equation of the oscillating plane in a particular situation.